Hello everyone, welcome to PSpice tutorials. In this session, I will simulate the input, output and transfer characteristics of an NPN transistor in the common-emitter configuration. I'll start with the circuit diagram first, and this in fact is the one. As you know, a NPN transistor in common-emitter configuration is connected in such a way that the input signal is connected across the base to emitter terminals and the output signal is connected across the collector to emitter terminals. So the emitter in fact is the common. Here we have two resistors, R in and R out. R in is also called as the base resistance and here is denoted as R1. R out is the output resistance which is RC or RL. We have denoted it by R2 here. The values of the resistors for R in are 5K and for R out I have chosen 1K. I have considered Q2N2222 transistor which is an NPN transistor for the simulation. Before I begin the simulation, I would like to let you know that I am not going to discuss the theoretical aspects of this configuration in this video. In fact, I have already made a video on that and I'll leave the link of that particular video in the description below. And I would highly suggest you to watch that first before you watch this video. With that, let us now continue to the simulation. I'll start with the input characteristics. Input characteristics are obtained by plotting the voltage across the input terminals that are base and emitter and recording the input current IB at a fixed value of voltage across the output terminals which are collector to emitter. Here I have divided the simulation into two parts. One for the single curve, the other one for the multiple curves. So for the single curve, I'll be using VBB as the primary voltage source and I'll vary it between 0 to 5 volts at an increment of 0.05 volts. Let us start with the simulation for this part first. I'll be using the student version of the Arcade PSpice software and I'm going to launch it by simply entering Capture Student. This is the application you should launch. I'm going to create a new project here. Right, the name of the project I will give as NPN in Common-Emitter new. Make sure that you have selected analog or mixed AD as the project type and you can save the location of all your project files wherever you want. I'm going to select them at a desktop folder. I'll create a new one for that. Select the folder of your choice, press OK, and now almost everything looks ready. I press OK here again. Then you will be asked whether you want to create the project based upon an existing project, which I don't want to do. So I'm going to create a blank project here. Press OK. To start placing the parts, you need to start by first left clicking on the schematic window and you see a new menu option would appear which is place. Select that, then click part. Right? So this is where you will have to select your parts. I'll start with the DC voltages. So I type VDC and you see VDC source is selected. Double click on that and you can start placing the parts now. Right? So I'm going to place it here and I want another one for the output signal as well. So I'm going to place it here again. Right? So now you can see the VDC source is still connected or attached to the cursor. Press escape and it will simply go away. Now I will have two resistors again, so I can go again to place and part. In fact, you should note you can do the same by simply pressing P for part from your keyboard. Right? I want resistors, simply press R, select R analog and place it at two different locations. Okay. Now I'm going to place the transistor. I need to search for Q2N. Right, it is already here. Q2N2222 is in fact the one I will be using for the simulation and I'm going to place it here now. I am now going to connect them by wires. In order to wire, you can directly go to this icon which is place wire or you can simply press W for wire from your keyboard and start connecting. Right, I have now connected my parts. What is missing is the ground. So in order to place the ground, press G for ground from the keyboard and select 0 source. Right, I'm going to place it here and I'm then going to connect that as well to my circuit. We now need to give values for the resistances as well as the voltage sources. If you remember in my circuit diagram that I had shown previously, the value of R1 was 5K and value of R2 was 1K. So I'm going to simply change these values. So double click on the icon that says 1K and change it to 5K. Similarly for R2, it is anyhow 1K, so I'm going to just retain it as it is. Okay, so this in fact is my supply, the first signal source. So I'm going to give 5 volts here, right, and I'm going to change the value of the same from V1 to VBB. Okay, so this is DC. Very similarly, I'm going to repeat the operation for V2 as well. Okay, and this in fact is our VCC. So the circuit is now complete. We'll start with the simulation. To simulate the input characteristics for the profile settings that I've shown here, which is for the single curve, I need to select the primary parameter as VBB, vary it between 0 to 5 volts in increment of 0.01 volt. So in order to do that, you need to simply go to PSpice menu option, create a new simulation profile. Right, I'm going to name it as NPN simulation. You can give whatever the profile, it doesn't matter. So create. Now you see a new pop-up window would appear. Here is where you are going to set the profile settings, right? So select the analysis type as DC sweep, because we are going to vary the input voltage here. Make sure the primary sweep is selected. By default it will be selected. Now come back here. You should decide what is your sweep variable. It is a voltage source, so select the voltage source. Give the name of the voltage source. The name of the voltage source is VBB. So I'm going to give it as VBB. You have to be very particular and very correct in giving the name. Otherwise it would provide an error. Right. So the start and end values can be given here. The start value is 0, end value is 5, and I'm going to increment it in 0.01 volts. Apply. Okay. Now we are ready to simulate, but before that, as you know, I want to plot the current. So I'm going to put a marker there. So this is the current marker. Select that and put it exactly at the edge of the base. Right? You can't place it anywhere, because if you try to place somewhere on the wire, you'll get an error. So it has to be exactly on the edge of the base. Right? So everything now is ready. Let us start the simulation. Right? I run it. You can run it multiple ways. One is this icon, the run icon. Otherwise, you can go to PSpice menu and there is a run option there as well. Now that I already have run it, you see there is a new pop-up window appearing. Select that. This is not in fact the input characteristics, because though the y-axis represents the base current, the x-axis is the supply voltage. You need to plot the base current with respect to the base to emitter voltage. So therefore you need to change the x-axis here. You can do so by going to the menu option plot, select axis settings, select x-axis, select axis variable, and now you have to select VQ1B. Right, which represents the base to emitter voltage. Press OK and press OK here as well. Right, so this is what you will get for the input characteristics. Please note, it is only for one single curve. If you want to obtain multiple input characteristic curves, which are simply by plotting the input characteristics for multiple values of the collector to emitter voltage, then you need to perform what is called as a nested loop operation. Right. So in order to tell you how it is done, I'm going once again to the profile settings. So this is for multiple curves. The primary voltage source remains the same, no change, but you need to now add the secondary voltage source, which is VCC. And I'm going to vary this secondary voltage source from 0 to 10 volts in terms of 5 volts. So I'll be getting two plots. Right. So I'll go back to my simulation window, select the simulation menu option and edit the profile. Right. So now you have to select the secondary sweep. Once again go to voltage source. Now you give the secondary voltage source name, which is VCC. As I said, I'm going to increase it from 0 to 10 volts here. So start from 0, end value is 10 and incremented with respect to 5 volts. Okay, press apply, press OK, run the simulation again. Once again you need to change the x-axis. So go to plot, axis settings, axis variable to base voltage. Right. So this is what you would get for multiple values. You can just see we have gotten three values here. One for 0 value of VCE, then for 5 value of VCE, and finally for 10 value. What should be noted here is that as the value of the collector to emitter voltage is increased, the transistor will turn on at a smaller value of base to emitter voltage. Therefore, the characteristic curve is going to shift left. So this last curve to the right will be for VCE equals to 0. The second one from the right is VCE equals to 5, and the last one is for VCE equals to 10. Right? So this is about the input characteristic curves. You should note that for the circuit what we have selected, the value of IB is positive because it is entering the transistor, and the value of IC is also positive and the value of IB is negative. Okay. Further, the value of base to emitter voltage will be positive because of the way in which the supply is connected. Very similarly, the value of VCE will also be positive because of the way in which VCC is connected. So, since VBE is positive and IB is also positive, we are going to obtain the input characteristic curves in the first quadrant. This in fact is our origin. Right? So, with that we continue to the output characteristics. The output characteristics are obtained by varying the voltage across the output terminus, which is VCE, and recording the output current IC at a fixed value of input current IB. We know that a transistor output characteristic indicates three different regions of operation: cutoff region, saturation region, and active region. I will be demonstrating the working of the transistor in each of these regions, and therefore I have three different simulation profiles created for the same. Right? I'm going to start with the cutoff region of operation. So in the cutoff region, obviously this has to be a nested loop operation because you are going to get multiple characteristic curves for the output characteristic. So I'm going to select my primary voltage source as VCC and secondary voltage source as VBB. And the primary voltage source is varied between 0 to 10 in terms of 0.01 volts, and the secondary voltage source is varied between 0 to 0.5 and incremented in terms of 0.1. Now, if the reason why we have selected 0.5 is because, as we have seen in the previous input characteristics, the transistor usually turns on at around 0.67 volts. So, any value of VBE less than 0.67 volts will make sure the base to emitter is not yet forward biased. So, the base current will not be sufficient enough to drive the transistor into either active or saturation, and therefore the cutoff region will be obtained. Right? So I'm going to start with the circuit again, but now I need to change my simulation profile. Okay, so first and foremost, I have to be very careful in giving these profile values because most of the times the way you select the primary and secondary voltage source is going to give you a proper characteristic curve. So I'm going to select my primary sweep variable as VCC. I'm going to increment it from 0 to 10 volts in terms of 0.01 volts. I'm going to select my secondary sweep variable as VBB. I'll be varying it from 0 volts to 0.5 volts in terms of 0.1 volt. Okay, so I make sure my readings and settings are correct. Primary sweep is VCC, secondary sweep is VBB, and the values of the primary sweep are 0 to 10 and that of the secondary sweep are 0 to 0.5. I press apply and press OK. Now I will move my current cursor from base to collector because in the output characteristics we are going to record the collector current. Right? So save the profile and run the simulation. Once again go to the pop-up window. So here I'm getting some characteristic curves, but the x-axis is not the collector to emitter voltage. So I change that by going to plot, select axis settings, select axis variable and select VQ1C, which is the collector to emitter voltage. Right? Press apply and now we are getting the output characteristics for a value of IB that is not sufficient to drive the base to emitter. You can look at this. The current is in microamps. That means only a very small, usually a leakage current is flowing through the transistor and the transistor is not in fact in the on state. Right? So this is for the cutoff region of the output characteristics. Now we enter the saturation region by changing the simulation settings. So for the saturation, I'm going to change my simulation profile a little bit. I keep the primary variable and the variation sweep the same, no change in that. But the secondary variable, which is our VBB, I'm going to increase from 0.5 to 2. and I will increment it in terms of 0.5 volts itself. So now you see the base to emitter voltage maximum is 2 volts, which is sufficient enough to drive the base to emitter junction into forward bias, and therefore you will observe that the transistor in fact goes into the saturation region, right? So to simulate that, I go to my simulation profile once again, and I'm going to select the secondary sweep, change it from 0 to 2 volts. I'm also going to change the increment from 0.1 to 0.5 here. So I'm quite expecting 5 curves starting from 0, 0.5, 1, 1.5 and 2. So 5 curves should appear if at all they appear, right? So press apply, press OK here and save the profile and run the simulation. Right, we are getting the current across the y-axis, but the x-axis needs to be changed. So I go to plot, change the axis variable to the collector voltage and press OK. Right, so now you can very clearly see the current has started to rise and it is now in terms of milliamperes, but the characteristic curves never enter the saturation. This is because the voltages applied across the supplies are such that the collector to base junction has forward bias, so has the base to emitter junction, and therefore the transistor is currently operating in the saturation. In order to send the transistor into active region, we need to increase the collector to base voltage, and for that I have created a final profile for the output characteristics in which the primary voltage source, which is VCC, is varied between 0 to 100 volt so that the collector to base junction can be reverse biased, and the secondary voltage, which is VBB, is varied between 0 to 2 volts in terms of 0.5. Right? So let us go and simulate that as well. In fact, I can change the simulation settings directly from the simulation window. Select the simulation, edit profile. Now I'm going to select my primary sweep, which is VCC, and I'm going to vary it between 0 to 100 volt. No change in the start value or the increment value. Then I'm going to select the secondary sweep value and make sure I'm varying it between 0 to 2. I'll change it to 0 to 3, so I will get more characteristic curves across the output. Press apply, press OK. Let us run the simulation again, and I will now change the x-axis to VCE. Press OK. Right. So this in fact is the complete simulation of the output characteristics of an NPN transistor in common emitter configuration. You can see when the value of the base current is very negligible and very small, the transistor will operate in the cutoff region. Here the cutoff in fact is almost falling on the x-axis itself and is not clearly visible because the y-axis is in terms of milliamps. When the base current is sufficient enough to drive the base to emitter junction to forward bias, we will start to obtain these characteristic curves above the x-axis, so that now the collector to base junction is reverse biased while the base to emitter junction is forward biased. Right? So the characteristic curve will move upwards as the value of the base current is increased. That is, if this is IB0, this will be IB1, which is greater than IB0. This is IB2, which is greater than IB1 as well as IB0, and it continues in the same fashion. Finally, the characteristic line what you're looking almost falling on the y-axis is what the saturation region is, and everything else where the current is almost flat is in fact the active region. Right, with that now we continue to the transfer characteristic of the transistor. Transfer characteristic is obtained by plotting the voltage across the input terminals VBE and recording either the output current IC or the voltage across the output terminals VCE. In order to do this, I have created a profile setting here. Since I am going to only vary the VBE, I need to only select the primary sweep, no need of secondary source at all. And the parameter itself is VBB. I am going to vary it between 0 to 2 volts in increment of 0.01 volt. Let us go and do the simulation now. So here I will edit the simulation profile, remove the secondary sweep, select the primary and change it to VBB. I'm going to vary it between 0 to 2 and I'm going to increment it in terms of 0.01 volts. So press apply, press OK. The current marker is already on the collector, so I need to only run the simulation here. Okay, so I'm getting some curve, but the x-axis is in fact the VBP. So I will go ahead and change the x-axis to VBE. So I'm going to select VQ1B, press OK, right? So this is what the transfer characteristic curve would look like. We note that when we plot VBE versus IC, we get an S-shaped curve, right? On the other hand, if I plot the output voltage terminals, which is VCE, with respect to VBE, I'm going to get a reverse S-shaped curve. I will simulate it again by drawing another plot. So I go to plot and add another window here, add a trace to that. I'm going to record VCE, right? So these are the plots for VBE versus IC, the lower one, and the other one is VBE versus VCE, the upper one. Since the output current IC can start to flow only after the input current IB starts flowing, we note that the collector current starts increasing at the same time the input current starts increasing across the base to emitter junction. At the same time, the collector to emitter voltage starts decreasing. Well, that brings us to the end of this session. To summarize, we discussed and simulated the input, output, and transfer characteristics of an NPN transistor in common emitter configuration. In my next session, I will discuss and simulate the input, output, and transfer characteristics of an NPN transistor in the common base configuration. Stay tuned to watch that session as well. If you like this video, press that like button and leave a comment. If you want to watch my future videos as well, you can always subscribe to my channel. Well, that's it from this session. Thank you for watching. Have a good day.